right, let's get started. Welcome everyone. My name is Mathieu. I'm co-founder and head of product at ShapeDiver, and I'm joined today by Edwin, our Grasshopper specialist.
Hello everyone, thanks for joining.
We're really happy to host the webinar and be able to share with you some of the things we've learned over the past few years while working on ShapeDiver. So we had an amazing response for the first webinar last week, so we decided to host it for a second time this week in order to give more people from different time zones the chance to attend. So in that regard, we must send all our gratitude to McNeil. They helped us plan and spread the word about the event, so thanks a million to the people at McNeil. So we'll host more intimate events in the future because you know, we had a lot of subscriptions for this first webinar, so involving each and every one of you might be a bit more challenging, but you'll see that we had some ideas to make the experience more interactive for everyone. But for the future events, please make sure to subscribe to our newsletter on our website if you want to be notified.
Yeah. So before we get started, we wanted to give a quick overview about our company. As some of you may know, ShapeDiver is an online platform for building cloud applications based on parametric models with Grasshopper. We work with over 12 different industries and have thousands of registered Grasshopper users. Some of our clients use our technology to build 3D product configurators for e-commerce applications, while others use it to build powerful internal collaboration tools. Why do they choose to do this, Matthew?
Yeah, well, parametric models have proven to be a very powerful tool for plenty of industries. But the biggest challenge has always been that most stakeholders lack the technical knowledge and the software needed in order to make use of them. So that's where cloud applications based on parametric models become a powerful solution to this limitation. By being able to access parametric models from any device and without the need of specialized software, more stakeholders can now take part in the decision-making process. So since we have been leveraging Grasshopper as a tool for cloud applications for a while, even a few years before Rhino Compute existed, over time we realized two things. On the one hand, many design principles and strategies we have developed are valuable not only in the context of our services, but in any context where parametric design is used as part of a cloud-based system. And the second point is that on the other hand, these principles and strategies are not natural to all Grasshopper designers, including experts. So that's why we planned the webinar around those observations. The idea is to raise awareness to the challenges and the bottlenecks that arise when Grasshopper is used as part of a bigger scale online application. So some of these concepts will sound like common sense, but others not so much. That's why we believe that those teachings can help in any context beyond cloud applications to work faster and better in Grasshopper.
Correct. So during this webinar, we won't be focusing on details regarding ShapeDiver, but rather on what cloud applications are and how properly optimized Grasshopper scripts can completely transform the way these applications perform, no matter the device used to access them.
Yeah. And so we have two main goals for the webinar. The first one is to share an understanding of the general principles for working with parametric models in a cloud environment. And the second one is that by the end of the webinar, we'll be reviewing some concrete use cases using ShapeDiver, and that will help illustrate the concepts we've seen over the webinar. So just to give everyone some motivation, I wanted to present a few examples of cloud workflows that leverage Rhino and Grasshopper. So the first case is an example of real-time collaboration workflows. Using tools like Speckle, for example, one can broadcast data, which is then synchronized and dispatched through a server to anyone who's listening to the broadcast. The data can be read through various desktop clients, not only Rhino, but also Dynamo, Revit, Blender, or even a web browser. In that case, the server is just dispatching data, but there are actually no CAD computations done in the cloud. But with other tools like Swarm or ShapeDiver, servers actually interface instances of Rhino and Grasshopper. And so it allows them to perform CAD computations in the cloud. So the first family of workflows consists of uploading definitions to a server online, and allowing various desktop clients, not only Rhino again, and web applications to remote control them and make use of the solution. So here the communication is bidirectional between the servers and the receivers. And if the cloud infrastructure is built as a fully scalable remote computation engine, like in the case of ShapeDiver, one can imagine more intensive use for them. So it doesn't really matter in this case how many end clients read and send requests to remote definitions. And that's the case, for example, for e-commerce applications, where Grasshopper is the engine behind product configurators that are accessed by thousands of people every day. And with a scalable server infrastructure, another workflow that can be achieved is to batch request multiple solutions from Grasshopper definitions and store them for further analysis or design space exploration applications. These type of operations could typically take days on a local machine, but it can be done in minutes with the right cloud infrastructure. The last point I wanted to mention is that, of course, some of these workflows can be achieved using Rhino Compute. Compute is a low-level API, which involves some custom development and to build your own infrastructure if you want to deploy it in a commercial environment. It's an amazing technology, and it makes things a lot easier for all the cloud applications involving Rhino and Grasshopper. And as a matter of fact, ShapeDiver will make heavy use of Rhino Compute from the release of Rhino 7. So in all these use cases that I went through, they have all very different goals, and there's different workflows involved, but there are some common aspects to all of them. First of all, the computation time of the Grasshopper definitions will always have an impact. In some cases, it might not be crucial, but in others, it really is. Second of all, in all cases, there is data traveling between servers and clients in one or both directions. So how can we make sure that we transfer the right amount of information depending on the goal? Moreover, how do we define data formats and input-output interfaces between the different parts of the application? And finally, how do we make sure that the parametric algorithms are able to run autonomously without human interaction on a remote server? So those 4 points are the 4 concepts that we'll see during this webinar.
Correct. So now let's give a quick look at our agenda for the next few days. In today's session, we will focus mostly on ways to make your definition faster and lighter. In tomorrow's session, we will look at ways to manipulate data in order to make definitions cleaner and introduce ways to set up efficient communication channels between Grasshopper and web applications. And finally, on day 3, on Friday, we will apply all of these concepts to a full automation example and demonstrate the results using ShapeDiver.
Yes. And if you got the reminder email yesterday, you might have noticed our daily challenges. So between each session, you'll have time to apply to the initial Grasshopper script that we included in the email some of the concepts presented by Edwin. So the idea is to optimize and organize the model in order to get it ready for a full automation workflow in the cloud. So that's our way to involve everyone, because the sessions will be quite dense and it might be difficult to follow with real-time hands-on Grasshopper work. So Edwin will give more details at the end of each session, and you should also have received all the materials we'll be using yesterday in the reminder email. So in terms of communication, we hope everything works as expected with Zoom. Let us know if you have any trouble with the chat. So I will answer most questions posted via the Q&A interface. So please use the Q&A interface if you have questions, because in the chat there's a lot of activity and I will miss some of them. I'll pass along the most frequent and interesting questions to Edwin so that he can answer them live. And at the end of each section, we'll also have a quick break where additional Q&A sessions can happen if time allows it. Once in a while, we'll also send polls to all participants, so you don't have to answer them, but we mostly send them to help curate the pace and the content of the webinar, so feel free to participate. You should already have received the first poll where we ask you your level of experience with Grasshopper. Concerning the daily challenges, we already presented the process in previous slides, so you should have been able to download the version 1 of the RIPS table model, and we will post the subsequent versions on our forum between each session. We'll create a topic actually on the ShapeDiver section of the McNeil forum for each challenge, and we'll be happy to chat and answer all questions there between the sessions. And Edwin will also give the solutions to each challenge at the beginning of the following session. So feel free to join the discussion on the forum, and also come back tomorrow if you want the answers to today's challenge. And as a last word, in general, we'll remain available for any questions besides the challenges. Between each session and after the last one, you can use the forum for that or the contact form on our website if you have a specific request. And finally, we'll be sharing a recorded version of the webinar around mid-May via our YouTube channel. So, make sure to follow us on YouTube if you want to get some updates about this. And that's it. So thanks again for joining us today. And without further ado, I'll let Edwin take the mic and get started with some Grasshopper work.
So thanks again, everyone, for joining. The first thing that I want to show you is the version 1 of the RIFs table. You should have received this table in the reminder email. If you didn't receive it or you didn't get this email, then it will be available in the forum. So where do you find the forum? If you go to shapediver.com/forum, there it will redirect you to the forum page of McNeil that is related to ShapeDiver. Here we will share, as Matthew explained, all of the daily challenges and all of the files that we will talk about today. So if you see for the first session, we had already some posts here, and here the participants of the webinar have been interacting with us, and we explain things or going more in depth in these forum posts. So here is the first table file. And something that I want to explain is these red groups that you see here. So these red groups represent the different challenges for the different days. So for example, here is for the second day challenge. So we won't look at this today, but there is several ones that go to the first day. So here we have the first day challenge, here another one. So after we explain all of the concepts today, you will be able to solve these challenges. But of course, again, just to remind you, the number 1 challenges, because the number 2 are for tomorrow, and in the third day, we will see something else. So here is this is the original file, and the idea is that we're gonna go and end up with the RIFs table final version. So of course, in looks and how it looks, it's the same. The geometry is basically the same, but then in terms of performance, it changes. So if we go, for example, to MetaHopper, that is one of the requested plugins, and then you go to Launch Bottleneck Navigator. Here, this is a very good way to start checking which components are the ones that are taking the longest, so that you can start optimizing your script. So for example, here we check openness, it's taking 4.2 seconds, make2d 1.8 seconds, etc., etc. However, this is regarding the actual production files of this table. If we go to our version 1 table, here we have that the one that takes the longest is this one, the difference component that is taking 2.1 seconds. However, here we are not generating any production data. This is just we are just grabbing data out of it, but we are not really generating any nesting files to be exported. So this file right now, this could be uploaded to ShapeDiver or to any online application right now. The problem is that it is not optimized, so it's taking longer than it should. It is not generating any exporting file, so we cannot get any material from this Grasshopper file, and we cannot also input inside it information that is valuable for us. So let me explain. If we go to the final version, this is a link that you should have received as well in the email. Here is the last version of the table uploaded, and here, for example, we have some good interaction control points where you can move this, and then the table will follow that shape. Then you have here some additional interaction, like for example, import your shape, where you can actually import an additional shape as DXF file. So for example, a heart or a star, and then that will be used instead of the base circle that we had at the beginning. All of this we will learn how to do it in the third day, as well as the last part here where you actually can download production files, download 3D model, etc., etc. So all of these we will see in the third day. So after all that, we can start with the explanation of the different concepts that we will see today. Just to be clear, we will explain all the concepts in simpler models. So we will not work directly on the RIFs table. This RIFs table is for the challenges, but we will explain the concepts that we will use in the RIFs table using these simpler examples. So to begin with, we're going to create not the entire house, but the general shape of the house, not the details of these windows and all of that, but the general shape. And to do that, I want to first make you a question. So if Matthew can help me out with this poll. So in this poll, we have, how would you start creating the shape of a house, in particular this house? With a box that gets deformed and cut with Boolean operations. So for example, if we have this box here, which is the base shape of our house, then would you use a Boolean operation? So for example, here, that's what we are doing. We have this box and we have this helper box here. And then we use a Boolean operations to create the final shape of my house that has this roof pitch, this roof angle. Or that's option A. Option B is to create each wall in the correct position and orientation. So that means you will start creating each of these walls polylines. So you will start creating each of the walls as polylines in the right position. So for example, this one is in the XZ plane, then you will create the next wall in the ZY plane, etc., etc. So you will start creating the box, the faces of the house from scratch. So that's another option. And the last option is actually that you will create each wall in the XY plane. So instead of doing what we just did, that you actually create each wall in the correct position as a polyline, we will create each wall in the XY position in the origin. So that means that if we have, for example, the roof pitch, so that wall will look something like this on the floor. Then over this one, we will start creating the next wall. So the next wall will be, for example, this long one in the side. So it will look something like that. But all of them are one over the other, and they are positioned in the XY always. And we will perform the actual positioning, the final positioning, just at the end. So please tell us which of these options you would normally use. Okay, so in this case, for this example, we use the number A, in which we're using this solid difference. So we have here the parameters of our house. We have house length, house width, house height, and roof angle. We use that to create our box. And the house height, we actually extended this house height so that we could actually intersect the house with this helper geometry, this huge cube here that will cut our house. Then we started to explode this component, but before that, I will first of all explain here. So one of the things that we've seen over the years that we've been working with other Grasshopper developers is that they normally don't use all the inputs that some components offer. So for example, this box offers a base plane, a X, a Y, and a Z domains. So for the size of this box. So to keep this script compressed, let's say, and organized, we try to always use all the inputs. So normally what we've seen is that they would start creating the box, then they will move it. So then they will move it in the Z direction, for example, of the house height. And so if we don't use this base, they will move it and then they will rotate it to end up with the same result. So they will move it and then they will rotate it. So we are creating like additional steps that we don't really need to have, because we can actually create the base plane from scratch. So here we have the XY plane in the correct positioning. So we know that this is going to be the position of our helper box is going to be X amount of units. In this case, 3,000 units. We are talking here in millimeters, so 3 meters above the ground. Then in the XY plane, and then I rotate this plane based on my roof angle. So in this case, 15 degrees. And then I'm performing all of these operations in my plane instead of performing the operation directly in the box. And that's the plane that I use here. And that's the one that I'm use here for the difference. So that's the first point, to start compressing your definitions by using as much of the inputs as possible of each of those of the components that you have. The second point is regarding this solid difference that we are using here. So this is actually not the most efficient way to create this house, at least the general shape of the house. It is very efficient when you are in the design process. So if you are using Grasshopper as a design tool to begin with, then it's very good to use solid difference if we go to the intersections. So we have here solid difference, we have solid union, solid intersection. All of these are components that give us a quick result, but they take a long time to compute. So if you are using it for design, it's good because they give you a quick result. But when you start to create the cloud application, so when you take your design and you start to create the Grasshopper version for your cloud application, you have to find ways to replace these components. So we never, well, not never, but the majority of the times, almost never, we use these components because they take a long time to compute. All of these ones that represent the interaction between two solids.
We want the answers to the poll, actually.
Yeah, so perfect. Can we have the answer from the poll? Exactly. So in this case, we have the 50% of the users, of the participants, will use the Boolean operation. So as I just explained, it's a very common components to use. But again, they are very computing expensive. So we will show you how you would try to replace these components with something different. But if you are creating your cloud application, please try to avoid all of these operations. So in this case, we're using it just for the demonstration. And then the next thing is to actually start to extract information out of this box. So if I deconstruct this box, so I use my deconstruct BRAP component, then I will start to do some operations on the faces of this box. So before I continue, I want to know this. How often do you use explode type components to get geometry from pre-existing one? Very often, every now and then, or hardly ever. So what I mean with explode type components is, of course, the deconstruct BRAP, but for example, the BRAP wireframe component, or the explode component, but the one that is used for the curves. So this component, so this kind of components where you actually explode some pre-existing geometry, some complex geometry, you explode it and then you start to extract from this geometry some, in this case, for the deconstructed BRAP, we're gonna start using the faces. So how often do you do it? Please let us know. In this case, well, we do this deconstruct BRAP component, and then we are gonna pick one of these faces. So we pick, in this case, we have a slider here, but we are gonna use the number 0. So the number 0 of these faces is the face on the other end of our house with the roof pitch. And then with that, we are gonna take the BRAP edges, the naked BRAP edges, so that we get all the boundary of our face. The problem here that we have is this component, the deconstruct BRAP component. So we normally don't use that. We normally create the geometry from scratch because the problem is that you need to have the most of control over the geometry that you are creating. Why? Because when you are using these components in your machine, in your Rhino, you have all the, let's say, the ideal situation for your situation for your script to work. But the problem is that if you are creating cloud applications with your script, this script is going to be used not just in your machine, but in other machines, in other computers, in other servers. So when you start to use this explode component, and then you go and you pick something from this explode component, the problem here is that you are picking it without doing any geometry check. So the problem is that in some computers, this number 0 face may be, as we have here, the end wall of our shape, but in some other computers or some other versions of Rhino, this number 0 face may be, for example, the one in the side, the long one. This happens. This happened very often, especially when there was the change between Rhino 5 and Rhino 6, in where some scripts started to get broken because some people were using Rhino 5, and then when they were using this for cloud applications, then in the servers, they were using Rhino 6, and therefore, if you were using this kind of just, okay, I want to grab my number 0 item, then in other servers, this was a different phase. So I have here, for example, two blog post where there is users from blog post in McNeil, where there is some users wondering about it, because here, for example, he can see that in Rhino 5 he has this result, whereas in Rhino 6 he has a different result. And the problem here is, for example, that he's using this explode component here, and then he's picking an item from it without doing any geometry checks. So what I mean with geometry checks is this option B that we have here. So option A is to just simply say number 0. Option B is to actually do a geometry check before you actually pick something. So here, if I take my face and I take the area of this face, I just want the centroid of my faces. So I just want the point in the middle of each of these faces. And then I want to pick from this centroid, I want to pick the centroid that is in the X coordinate in the same location than my house length. So because I know that this wall is the one that is in the other side of my house. So in this case, for example, I take the house length, and then I do even go more with this, because I don't go, for example, with equal. So if we go X equals the house length, that means that there should be at least one that give us true, because here we have 5,000 is the number 0 is 5,000, and this one, then in this one my house length is 5,000 as well. So it's supposed that we should get one as true, but when we go here we get all of them as false. Why is that? Because of the tolerance. Because different machines, different computers may have also different tolerances. So when we use the similarity here, we're actually giving a higher tolerance of, for example, in this case, 0.1. Sometimes the default tolerance is like 0.01 or 0.001. So there's a very, very small tolerance. And in this case, we are using a higher tolerance to actually get our first one as true. And that's what will actually cool our list, and we will get the item that we need. That is this one that we picked here randomly instead of doing a geometry check. Then with this face, so again, if you really need to use these explode components, you need to make sure that you do a geometry check or a mathematical check after this explode component to make sure that the item that is being selected is the one that you really want, so that when you use it in a cloud application, it is stable in any machine that it gets used to in. So we're just gonna make our model more stable. And finally, here we just take the boundary of our face, and then here I'm just doing let's say like a window for our face. So we just put this window on the other side of the wall again with the house length, and then our window is 1,000, so 1 meter away from the edge of the wall and 1 meter away from the ground. So we have here our window, and from that I merge these two components, and we get our, say, one of our faces with a window for this example. So this is some recommendations that I have for you in the normal way that you would construct this house, but there is actually a more optimized way to do this, and I will look into it. But first, I want to know what was the result for our second poll. Please, Matthew.
Yes. So as expected, a lot of people like explode components. They are easy to use and produce good results usually, but you just have to be careful, as you explained. Correct. So you just have to be, if you really need to use them, just be careful, because again, you need to make sure that the face that is being selected is the correct one. So this is normally a workflow that we've seen very common in the Grasshopper community, and again, it's very good if you want fast results, especially if you're in the design phase of your Grasshopper model. But if you then start to create the Grasshopper definition that needs to be used in a cloud application, you need to make sure that this is the most efficient and the most stable as possible. So another way to do this same phase that we have here is to actually use our C option. So our C option is to create each wall in the XY plane. So let me explain how that looks like. So here we have a component called the right trigonometry component. So yes, this is a bit of math that we are going to use here.
And normally, the best friend to create very optimized models is normally maths. Using maths can really help you out in the creation of optimized models. So in this case, for example, we are creating each of the points. If we go to the top view, we're creating each of the points for our face. So to do that, of course, we have the origin point here. Then we have the house width. So that will be in the X direction. That will be this second point here. Then we have, that will be the origin. Then we have the other point in the X direction with the house width. Then we have our next point is actually because we need to get this. That's why we use trigonometry. So if we have our house height. So our house height is this one, but we need to also calculate this other part so that we can actually get the total height of y coordinate of this point, of the point that we have here. So this one we already have it. So is x0 and y equals the house height, but the last one, the one here, is the one that we need to really calculate this height using trigonometry in this case. The good thing of the right trigonometry component is that it's very visual, so you can actually know that here I want to get the q length, and here you can easily input, well, what is your alpha, so that will be your angle, and the house width, that will be p. And with that, you can get that information. And finally, well, as I said, our last point, with that we get all of our points, we create our polyline, and with that polyline, we can start creating the surface of our polyline with our window. So here I have a similar window. In this case, is, let's say, a door, because it's on the ground. I will demonstrate why I put it there first. So here, one option A, is to take our boundary and our door or window, and then use the boundary surface component. The problem here is that this boundary surface component won't give us the right hole here, because our both the rectangle and the polyline are collapsing. So here they are collapsing in the same space. But for example, if you put just one unit above the ground, so in this case will be y, then you can see here that it is just one unit above, and therefore our hole is created. But of course, that's up to, like, because again, if this is just for visual purposes to begin with, then maybe this one unit of difference won't make any, let's say any issues for you in terms of how your model looks in the cloud application. Or the other option is, if you really need this to be exact, then you can use the region difference component, where you actually take, so if we go again this to 0, so we delete this one. We actually take this rectangle and we take the other one, and the region difference actually computes our hole and computes our final boundary width that creates the correct shape of our house face. These components, this region difference, region intersection, and region union, they are a bit faster. However, there is some bottlenecks when you start to use too many curves in each of these inputs. We will see an example tomorrow where you can actually, through data trees, make these components even faster, these region difference components. But for example, here, if we know that this is going to be, I don't know, a window, for example, then we can make this window. Okay, let's use this 1000 here. We can use this window 1000, so 1 meter above the ground, and then our region, our boundary surface works perfectly. Again, that depends on what the use case, and how many curves you are using, etc. And in this case, well, with that we create our boundary surface, and just at the end is that we actually orient this in the same position that we have, for example, here, this other face. So here, if I select this one, it's the same than if I select this one. And the reason why we do it everything in the XY plane is because everything is predictable. So I don't have to take care of, oh, is my face in the YZ position, or is my face in the XZ position, or where is it? So that I know that when I put other object oriented to this wall is going to be in the same orientation than my mother geometry, let's say. Instead of having all of this in the correct position from the beginning, we make everything laid down on the origin so that everything is predictable, everything is easy to use. So all the time we are using the X coordinate, all the time we're using the Y coordinate, adjust until the end, is that we actually position everything in the correct place. And in this case, of course, we will use data trees to start to create each of these walls in the ground. So we will see here, instead of a single tree with 4 points, we will see a tree with 4 branches, because we have four walls, and each of these walls will have 4 points that are the points that construct our polylines. So we'll use here data trees. The data tree, we will check that tomorrow, and create each of these walls here and just position until the end. So this is how we would do it, creating from scratch each of these walls. So this is the first part, our first example. So I want to know so far if there is any questions.
Yes, a few. A lot of people want to know what software you use for drawing lines on your screen and showing stuff.
Okay, that software is called Epic Pen.
Okay, someone had found the right answer. Perfect.
Yeah, Epic Pen.
Okay, good. Another more simple ones. What is the right triangle component? I think they mean the one used for trigonometry, probably.
I don't have any information about that. Do you want to know what the parts of a right triangle?
Sorry? Matthew? Okay, so if they are talking about the trigonometry component, this one is the trigonometry component. Yeah, that's the question, Matthew?
Yes, perfect. The rest of the questions is mostly about what to do, what to do if you have to use Boolean. So basically, someone asked, can we expect the computational efficiency of Boolean operations to improve in the future or work better in the cloud? Do you believe it's always possible to replace Boolean operations with other components?
Maybe it is not always possible, but there is always a better way. So, for example, here in the forum, there was one participant of the last webinar, and he actually had a question regarding quite let's say computer expensive Boolean operation. Let's see if I can find it quickly. Yeah, here it is. Correct. So in this case, he wanted to have one shape and then have a Boolean operation of this shape with, he was saying, 500 other objects. So in this case, for the sake of this example, I used a sphere and a set of spheres to do a Boolean operation in the main one. So in this example, for example, I show option 1, option 2, and option 3. So there is 3 options that I use to compute this. And for example, with the solid difference, it takes 2.8 minutes to compute. Then we have an option 2 into a cluster. So if you want to know how much something takes in total, you can cluster it, and then that will give you the total that it takes to compute. And then this one takes 2.2 minutes. And then I have a third cluster, a third attempt. And this one gave me 8.3 seconds. So almost having the same result, I went from a 2.4 minutes computation with a Boolean difference to a 8.3 seconds computation with this cluster. So you can come here to the forum and you can download this example and see what I did inside this cluster. Anyways, I suggest to him that you could even continue down the track and to continue to think of even better ways to make this even faster. So there is always a way to make the computation faster.
I think there is always the problem with Boolean operations, as I answered to one participant earlier, is that they're implemented very generic, so that they solve
exactly
with precision and efficiency any case. But you know, if you look at each single case and you study each single case, you can find a better way for this case that gets solutions faster. Of course, sometimes it might be more or less difficult. So that's a problem. For example, one participant asked, for instance, I'm making heavy use of text in a current project where I need to engrave text in a predefined geometry, a ring. So that's like typical for jewelry applications. And this, correct me if I'm wrong, I think we'll show a way to do this with one of our scripts later.
Yeah.
Yeah, perfect.
Yeah. And another option is actually this this plugin. Do you remember the name, Matthew? The plugin that use volumes instead of solids.
Yes, there's a plugin we support on ShapeDiver called Dendro, Dendro, which yes uses volumetric representations to do Boolean operations. And we didn't test it a lot, so you know, take it with a grain of salt. But a lot of people like it, and it seems to be very efficient to try to do Boolean operations. So if you want to try it, you can install it and see how it works for you.
Exactly. So this one is a bit faster, but again, as Matthew said, it may not be as stable. Okay. Any other questions, or can we continue?
No, you can go on. It's not related to the topic for now.
Okay, perfect. So this one was the first example where we show some methods of making your definition faster, and then we're gonna go to the second example. So we're gonna do a perforated wall. In this case, this perforated wall, I'm using this puppy example here, and then at the end we get something like this. So if we go to the top view, we get something like this. Here we have the inputs. So we have some standard drilling radius. So we use this one because normally in architecture, especially if you're doing a drilling wall, there is some standard radiuses. So it is, unless it is a 3D printed wall or something, there is always some standard drillings options that you have for your wall. So in this case, we have these 4 options of drilling radiuses. This is just example. So this is not a precise radius that they are using for fabrication, but it's just example. Then we have some perforation max size, perforation min size. So that means the domain in which our circles will be created. So if we use smaller circles, then we can see how our definition changes with smaller and smaller circles. And if we use the biggest one, well, then it will use all the range of radiuses that we have. And then we have also the same for this. So if we go to the other side, then we're using bigger and bigger circles. And finally, we have the wall size. In this case, for the sake of keeping it simple, we just made a single wall size. So it is the same wall size for the X direction and for the Y direction. So for the width and the height of our wall. So basically here we are just doing, yeah, here we're just creating a grid. So if we check this grid here, so that in this grid we know that one of our drilling holes can go. So this drill, the size of each of these quads in this pattern is as big as the biggest perforation that we can allow to have, and plus some gap, so that we avoid any intersection between different drilling holes. So that's what we do, this sum up, and then we do the division with the wall size, so that we know how many drillings can we have in both directions, in the height and in the width of our wall. So we have here the number of quads. So in this case, it's 43. And here, when we divide this by the wall size, that we get the size of our quad. So quad size is, in this case, 93. So with that, we create our base grid for our pattern, and we also create a secondary one that has a size of 1 by 1. This is just to sample our image. So we know that our image, well, we can also change this domain. In this case, I'm using the default one, 0 to 1 and 0 to 1, and that's why our grid here is 1 by 1. And with the centroid of each of these quads is that I actually sample my image, and with that sample, I get the luminance of each of my points, of my sample points of these colors. And with this luminance is that I actually defined how big or small my perforation is gonna be. So that's why I remap them here. So here we have the luminance, and then we remap that from the minimums and maximums. So I think this would be 0 to 1 in the bounds. Oh, come on. In the bounds. Yeah, something between, somewhere between 0 and 1 is our bounds. And then here we have, we are gonna remap it to the perforation mean size and the perforation max size divided 2, because again, we are talking about the radius. And with that is that we get our final radiuses for each of our perforations. So here we have a list of all of those radiuses, but then we need to round to nearest, because we need to make sure that each of these perforations is actually inside our standard drilling radius. So all of them will be snapped to the closest standard drilling radius that we have. And that's when we get here our final result of radiuses with 30, 40s, 10s, etc., depending on how near it is to one standard drilling. And with that is that we use our original grid, the original centroid of our original grid. So we take our grid, we take the centroid of each of these quads, and with that we get the circles. So we take the final drilling radius and then the plane, and then that gives us our final circles. Now, what we need to do now is to convert these circles into a surface, into a solid. So there is different ways to do it, and I want to know how would you normally do it. So how would you convert the curves into a surface with the drilling holes? So would you normally use the boundary surface, the surface split, the solid difference, other? Please let us know. So Matthew will help me out with a poll here. In this case, I have here a surface split and a boundary surface. I'm not gonna activate them right now because in the last webinar I actually did it and Rhino crashed because it actually takes a long time to compute. However, I took a screenshot of it, and you can see here that the boundary surface actually takes 15.2 seconds to compute, and the surface split takes 5 seconds to compute. So you can split your surface. And then, so for example, here we have two options. So with the first one, we're actually making it 3 times faster. But then after that, of course, we have to, because we're gonna get all with this surface split, we're gonna get all of our surfaces, including the drilling holes. So after that, we actually need to, maybe with the area component, again, because we shouldn't just take geometry like from an index, but we should check geometrically which geometry we are taking. So we could, for example, take the area of each of our surfaces, and then the biggest area is our final wall. So again, we're adding more and more computation to our wall. So can we have the result of this one, or shall we wait a little bit more?
We have mostly boundary surface. Yeah.
So as you could see, this boundary surface takes 15.2 seconds to compute. So boundary surface is really good when you have very few cures, but when you start to get very complex with all of these cures, so for example, here we have how many circles? 1,849 circles, and plus the rectangle, of course, then that starts to scale up to a huge amount to compute. So we have another option to do this. Another option to do this, we have it down here. So the first thing to have into account is this area component. So in this case, is taking just 10 milliseconds and 16 milliseconds to compute. However, sometimes, again, if you start to get more and more geometry, the area component is normally not the most optimal. You have to, I mean, depends on the case. In this other case, I'm actually creating the points from scratch. So instead of creating the grid and then taking the centroid, I'm actually taking the quad size. So I know my quad size and I know my number of quads. And with that, I create a series. That series, I move them in the Y direction and in the X direction. Of course, starting in the quad size divided 2. So because we want the centroid, so we want it to be moved half of the size of our quad. And then we graphed our X coordinate so that each of our X coordinates get moved in this case, these 43 times y coordinates that we have. All of this is regarding trees. So with that, we create our points from scratch instead of using the area component. That's the first point here. And then the main part that we're gonna use here is we're gonna create just the surfaces of our standard drilling holes. So we have here standard drilling holes. We create the circles in the origin. So again, we're keeping everything in the origin. That is very predictable. Then we create the base quad. Okay, that is, of course, this quad is the same size that our grid quads. And then from these ones is that we actually create, so we group this. So we have here all of our quads and all of our circles. We group them here in 4 branches. So we have four standard radiuses. And then we have our output here, 4 branches, which have the circle and the rectangle. And with that, we create the standard surfaces. Now that we have this, so we just compute here 4 very simple boundary surfaces. Now we need to move these boundary surfaces based on its drilling size. So here we're gonna use the same one, this final drilling radiuses. This is already rounded to the standard drilling radius. So we have this one down here. And then we have again our standard drilling radius lists. Then I'm gonna use this list to find to which member each of these standard radiuses in our complete wall. We have all of these points with different radiuses, and I want to know to which standard radius it belongs to. So here it gives me the index. With that index, I can actually use this component called the replace path component that will group all of our different points in the different standard radiuses that we have. So here as input, I actually flatten my final drilling radiuses. Then I get a tree with the same amount of branches as we have of points. So we have here 1,849 points, and then we have the same amount of branches here. And then with that, I take my points, which is the same amount of points. And then with that is that I actually group them in the different branches that we have. So we have now, again, 4 branches. Each of the branches of branch 0 represents the standard radius, in this case, 10. The next one, the number 1 represents the standard radius 20, then the next one and the next one. So here we have all of our points grouped based on their standard radius. And then with that, we can actually take our four surfaces here, which are also in 4 branches, and 4 branches here as well. We take this geometry inside here, and with that, we actually get our pattern, but it's taking 135 milliseconds instead of taking the 15.2 milliseconds that, for example, our boundary surface was taking. Now, some of you may wonder, okay, but now we have all of these separated into different surfaces, you know, like each of them are different surfaces. And this is when you have to think about whether you actually, because then we can actually join this or make a BRAP join, and convert this into a single surface. But this actually takes a bit of computation as well, and you don't need to do it because this is just for visualization purposes. I will talk more about it a bit later when we start to talk about meshes. But in this case, we want to visually get the same result. However, there is an option B to create this. There is an option B. And this is like, say, our secret sauce is our secret, well, it's not that secret because we actually have this C#, all of these C# scripts available in our blog posts. So we have written some blog posts, and there we share all of these information, and we also share all of these scripts. It will be also available in the forum post that we will create regarding this first day of our session. And what this component does is the following. So here I have my surfaces in 4 branches. So I will put that into the geometry input. And here I have something called the X form, so the transformations input. So instead of using this input, instead of using the geometry here, sorry, instead of using the geometry here, so I don't need to anymore move my geometry here, because the only thing that I need from this output is the transformations. So I need to know how much each of these surfaces are gonna be moved, are gonna be transformed in this case. So we have 4 branches here and 4 branches here as well. And as output, so if we put this here again as output, in the geometry output, we get 1,849 surfaces as output. However, if we check here, we're actually getting the same output. So we're getting four items as input and 4 items as output. So if we check this, we actually, it seems like we get the same. So we have the same surfaces here and we have the same surfaces as output. The only difference here is that now these surfaces have internalized metadata, which includes these transformations. So when we input here, in this case, the ShapeDiver display component, this component already can read these transformations because this C# is especially for ShapeDiver. However, if you have other applications, try to do something similar. So when we input this into the geometry input, oops, we can see that we get the same result that we would do if we input here directly. The difference here, the big difference here, is that we are sending to the online application just 4 geometries, just 4 pieces of geometry, which are very simple, just 4. And the transformations happen in the viewer, happen in the browser. So instead of we sending all of this geometry, which is very heavy, we're sending all of these faces and sending them to the browser, to the cloud application, all in once. This takes time to be sent, to be transferred, and also to be downloaded by the browser. Instead of doing that, we are just downloading 4 surfaces in this case and making the transformations inside the viewer, inside the cloud application. That's way faster because the transfer of data is way faster, and we are creating just 4 meshes in this case. I will explain about meshes later. And in this case, and in this way, is that you can actually make your definition way optimized. Of course, here in this case is that when we have to start thinking, okay, this is for display purposes, but what is for production purposes? So what do I really need to produce? What do I really need to make this something that can be produced? You will normally, from this definition, will export the circles, but you don't really need the actual 3D. The 3D is just for visualization purposes of the online application. But as export, you will just simply give the circles. Then is when you start to separate your definition from what is gonna be visualized, that has to be as most optimal as possible, and what is gonna be produced, which is in another branch that we normally activate just until the end when the definition is finished. When somebody finished using the online application and then they go, okay, I want to produce this, then is when we activate the heavy duty that is all related to production. We will see this more in depth in day 3, so on Friday. And with this we end the part regarding optimization, and we will start with the meshing section. But before, I want to know if there is any questions.
Yes, mostly people asking, if the case is not exactly a planar surface like you're dealing with, but a freeform surface, for example, and these kind of more complex cases. So in that case, you wouldn't be able to use exactly the same workflow, but probably you can find some other ways to optimize it.
These are just simple examples, of course, to show you that there is always a different way to do the same, to have the same result. But of course, if you have a more complex one, like for example, right now we are gonna look at a surface like this one. Let's say that is more free form. Then you will use different methods. yeah, for example, if I want to put some holes in this, and just thinking right now how I would do it, probably I would start by trying to project. So let's say we have our grid here of circles here laid down on the ground, and then I would project these circles into my surface, and then use the split component, the split surface component, for example. So it's just something that came to my mind. Then you have to, of course, try it out and see if maybe it's the most optimal way, maybe there is another way, but in that way, that's, for example, a solution. Instead of using the Boolean operation, you will use the projection and the split VRAP, the split surface operation instead of the Boolean that is more computing expensive. So then you can try it out and then iterating and try to find even better and better ways to do it. Mm-hmm. Any other question?
Yeah, several users remark that what we could send to the servers is basically just the coordinates of each centroid of the 4 face types, but then you would still need to send the geometry, right? The 4 different types of holes. So these 4 different meshes. Mm-hmm. But of course, since it's a rather simple geometry in this case, you could also try to replicate the geometry with web technologies after the definition is uploaded. That's another version, but it's, it requires some custom development on the website.
Yeah.
With the method that Edwin just presented, you can do everything with the Grasshopper definition, and mm-hmm. You're done.
Yeah. I mean, that option is really good. Then therefore you are using just Grasshopper to, let's say, to extract information out of it, but you don't extract geometry, and then you create the geometry in the cloud application. That's an option.
Mm-hmm. Yeah, that's it.
Any other? No? Okay, perfect. Then we can continue. So far we have been talking about optimization and ways to make your workflow more optimized for cloud application and more stable. And now we will start with meshing. So something very important to have into account. So every single time you send a VRAP to ShapeDiver or to any other online application, all of them, in our case, if you send VRAPs, we automatically convert these VRAPs into meshes. The reason is because, for example, here we have these example curves here. If I then do a loft and then I bake this into my Rhino, and then I go into my set view, into my display, and then I go into the rendered viewport. Then we select this and we go what? Mm-hmm. What happened? Okay, there we go. Doing well. Then if we go what, then you can see that even though we have a NARF surface, our render is actually a mesh. So all the time that you are actually meshing something, when you are actually rendering something, it actually needs to be meshed. Why? Because our graphic card is always looking for primitives. So primitives is those who are normally into the rendering industry, they don't call these polygons. So we normally call them polygons. They call them primitives. And this is what normally our graphic card is looking for, to create the pixels that we see, to create the geometry that we see. So we have the primitives here that is our quads in our mesh. Then we go through the process to get it rendered. So in this case, because we give it a VRAP, our Rhino is automatically converting this into a mesh, and we can see here how many vertices there are and how many polygons there are. The problem of this is that here, therefore, this is copying in automatically, and then therefore we are not controlling this meshing process. And this meshing process also takes time. And the bigger your mesh, the heavier your online application will become. So we have to make sure that our meshes are as low poly as possible, but of course without compromising how it looks. For that reason is that we should always send to any online application meshes that we create. We control how they get created. And for that, well, first of all, I want to ask you, how often do you work with meshes in Grasshopper? Very often, every now and then, or hardly ever? So that we can see how used to are you how used to are you to actually working with meshes? So the basic, so normally those who are in the jewelry industry normally use a weaver bird. Weaver bird is always using meshes, but in other industries you are more used to working with B-wraps. Anyway, so in this case, we're converting this into a B-wrap, and then the basic way to convert this from B-wrap to mesh is to use the mesh B-wrap component. So with the mesh B-wrap component, you have the B-wrap input, and you also have a settings input. So the basic way to mesh this is to use the speed settings input. This will use, well, the settings that are the fastest to compute this mesh. And then we go Control M, then we can check how our mesh is being created. So we can see all of the quads, all of the vertices that our mesh contains. And then if we create a panel here, we can see how many vertices and faces our mesh has. So it has more than 1,000 vertices and more than 1,000 faces. As if you remember, when we rendered this into Rhino, it was creating a mesh that was, I think, more than 3,000 vertices. So just by doing this, we're actually controlling now more our mesh, and therefore we can bring down our face count and our vertices count. Now there is something called the custom settings component. If we use this one, with this one you can actually control even more your mesh. So here we just went from over 1,000 to a third of that, 500 vertices. So that of course starts to, let's say, starts to play around a bit with the final result that we want. So maybe we're pushing it too much, or maybe not. In this case, if we see the original one to the mesh one, is very similar. So in this case, the difference is almost none. Therefore, it's a good solution to keep our mesh as optimal as possible. We can even play here with the minimum edge and maximum edge of our mesh. So for example, if we start to move this to the maximum one, then we will start to create bigger and bigger faces. So we check here minimum. Okay, so here we are saying that the minimum edge that this can have is 136 units is the minimum edge of our faces. Therefore, of course, our mesh quads start to become bigger and bigger, and then again then is when we have to find the balance between how optimal I want it and how do I want it to look. So of course here maybe that's already pushing it too much, and then we start to get something that is too low poly, and then it starts to affect our design. Again, this is just for visual purposes. Then if you want then and then you separate the part that you want for production. So for visual purposes, you will try to control that your mesh is as low poly as possible. So this is one way, is to use the mesh B-wrap component, but there is a second way. And is using, again, a C# script that we developed. There is also some plugins that already have similar solutions. This one is our solution, and you can find this C# again in our blog posts or in the forum post that we will create of this day one. So here we have again the same original curves. I'm using this twin consecutive curves component of pufferfish, and here I'm using the wave to take my original one and my twin one, my original one and my twin one, so that we have, because here what I'm trying to do is to create my wireframe, the wireframe of my mesh from scratch. So the wireframe is all of these the different points where my mesh will be created. So I'm trying to create my wireframe from scratch. So we have again here two options. One is, first of all, we need to convert these. These are curves, planar curves, and we need to convert them into polylines because we need points in the space so that our mesh can actually start to create each of these quads. We need these points in the space, and a polyline is basically a list of points. And then for this component in particular, we need the same amount of points in each of these polylines. So if we go explode component, we put it here, then we can see all of the different points there, but we can see that we have in some of these polylines we have 25 points, in other ones 17, 16, etc., etc. And the problem is that we need actually the same amount of points for this component in particular, because we need that each point has its correspondent point in the next polyline curve, and in the next polyline curve, and in the next one, so that we can start to create our mesh from scratch. So we use here the compatibilize polylines component. This is also of pufferfish. Here you can see it, pufferfish, and here it is. And then with that, if we explode this one, we actually can see that now all of them have 33 points. And then when we use loft mesh C# component, then we can see that our mesh is created. So here the problem of doing this compatibilize is that, again, we are not controlling where these additional points are being added, and therefore we can create, we end up with a kind of weird mesh that sometimes can end up with some problems if this, for example, starts to shift too much. If the position of my original point starts to shift too much from the next one, then we start to have some problems there. So the second option is the option B, where I actually take my curve, then I take and I divided all of them. I divided by 30. So I know that now I have 30 points for all of them. I don't have to use these compatibilized polylines. Then I create a polyline from that, and then I input that into my loft mesh component. And then this creates from this, it's like creating my wireframe. I create my mesh, which is way cleaner. And we can check also, well, the output mesh, how big it is. So based on this amount of points, on the amount of polylines in this direction, so is that we can know how many, we can control how many quads are gonna be in our mesh. So in this one, we don't really control, we don't have full control of how many quads. However, in this option, we have a bit of more control of how many quads there are gonna be in our mesh. And then with that, we have also this wealth input component. In this case, I'm using 2 multiplied P, so 360 degrees. And this wealth, what it's doing is, here I have the explanation. So basically, is comparing what is the angle between one particular edge and its neighbor edge. So it's the next edge that is from this one. And with that is that depending if it is in between this tolerance of 2 multiplied P, so in this case, this tolerance means that everything will be welded. What happens is that if we see here, this one actually has 2 normals in each of these vertices. So each of the vertex contains 2 normals. Therefore, our light, if we can check here, our light reflects in different directions of our mesh. So our light reflects depending on the normal direction of our mesh. So in this case, because we have different directions, therefore we can see a seam in our mesh. However, if we weld it, that means we are joining our normals into one single one. Then we have now just one single normal in each of these vertex. And therefore, our light is reflecting in the same way, and therefore it simulates that our mesh is smooth. So I don't really need to, in this case, for example, I'm simulating this smoothness with this welding instead of creating let's say a more detailed mesh. So because you could start to create a very detailed mesh so that it looks smooth, but with this solution, you can actually fake this smoothness. And also, on doing that, you can also help in the optimization of your online application. And that's the difference between having something that is completely not welded to something completely welded on the other side that is completely smooth. Then I want to now start to check how we would start to mesh our previous examples. But before we do that, I want to check if there is any questions.
One is there any difference for ShapeDiver between triangular and quad mesh for computing? There's absolutely no difference. Just use the meshes that make sense for your application, and depending on how you build them. but the meshes are sent by the servers to the to the front end in any case, so it doesn't change anything. And okay, then now I get a lot more questions, but one has been here for a long time, which is about scripting, and we'll keep it for the Q&A session after it ends because it's not directly linked to meshing currently. What about situations where you're starting from a mesh that needs to be optimized?
Good question. Well, there is some rebuild components, but they are not really very good in the Grasshopper. So there is the rebuild mesh components, but they are not really good. And but yeah, I mean, I haven't thought about that one, to be honest.
Well, I mean, it depends a bit what the question means, depending on if you start from a static mesh that you can internalize or reference, and then of course you have control over, how detailed and how how the meshing, the topology of the mesh is from the start, right? So of course you should make sure that the mesh is does not contain too much information and is just enough for the application you need. Then if you can't really control that, for example, there's a link question. One of my definitions need to import a mesh from a 3D scan, for example. Then if you do have to process the mesh inside Grasshopper, then that's always gonna be computationally intensive, because just like reprocessing, reducing meshes, etc., is very computationally intense. So the advice is, as much as possible, this operation should be done as a pre-processing operation before it's used in ShapeDiver, in Grasshopper, because Grasshopper is not really meant as a tool to like reprocess your meshes in the first place.
Yeah. And anyways, we will check into that in more detail on Friday, because we will actually use some components to import external geometry, external meshes, and then we will explain more about why your meshes have to be, even if they are coming from if you're not creating them in Grasshopper, but they actually are coming from somewhere else outside Grasshopper in your online application, then why you have to keep these models also as optimal as possible.
Yeah, so regarding the 3D scan, someone is saying that they need to import a 3D mesh, but then perform Boolean different operations between them, which we don't recommend if you can avoid them. So they're asking if it's better to convert the mesh to a brep and then do Booleans between breps, or use a mesh Boolean operation. I mean, in general, converting a mesh to a brep is very difficult, and there's some plugins to do this, but it's not
Pufferfish, for example, has that.
Yes,
but they are not they are not the most stable.
No, yeah, exactly. It's not something that I would recommend to do. So then you do have mesh Boolean operations, but same thing, they're going to be really computationally expensive. So I think it's a bit linked to the last topic that Edwin will talk about, which is that it depends what you want to do here, if it's for production or visualization, and you can maybe save the Boolean operation for visualization purposes and only execute it when you really need to create the production data.
Yeah. Anyways, if your mesh is coming from somewhere else, or if you have a mesh and you have to do some intersection in this mesh, something that is very optimal to use is, for example, the mesh plane component. That one is really, here we have it in the meshing. There is one called mesh split plane component, which splits our mesh based on a plane. So if, for example, this is very, very optimal. However, has a bit of a problem, because if the plane is exactly in the same position of a vertex, then it can kind of break the solution, the final solution. But if you can use this splitting of meshes by a plane or by a plane, it's very optimal. We have also a C# component that actually extends this solution, because we actually we had to operate in one of our projects. We had to operate into a mesh, and we used a lot this splitting, and for that we had to extend our this solution that the Grasshopper has, and we actually have a C# that splits a mesh with a list a list of planes. So this is like our bucket of C# script. Yeah, here it is. So mesh split planes, and basically you give a planes, but you give a list of sorry, you give a mesh and you give a list of planes, and as output you have a list of in the same order of the different sections of your mesh. So this is, for example, an alternative if you have to operate on your mesh. Try to do it with planes. It's quite optimal.
No more questions for now.
No more questions. Perfect. So finally, I just want to show how we would then, therefore, knowing all of this that we just did here, how would you then send this as a mesh to your online application? So here, for example, we have the front wall, so the same one that we created before here. If we see it in the same location, here it is, and then this is the same one, and I'm just gonna on the XY plane, and I'm just gonna extrude it. So because we want to, of course, to make it realistic, to give thickness to our wall. And again, here is, for example, one of the benefits to have everything in the XY plane is that now every single time that I want to extrude something, I always do it in the Z direction. So I don't have to be thinking of oh, and this one has to be extruded to the X one, this one has to be extruded to the Y direction, but all of them get extruded to the same direction, to the Z direction. And then I use the first option, that is to use the mesh BWrap component. In this case, it's a very simple geometry. Therefore, this component is quite fast to create a solution and creates a quite optimal solution. Because everything is very orthogonal, it's not very organic. But there is a better solution in which you can avoid creating BWraps. In this case, we take again our final wall surface. And okay, so there is a solution first of all that I had to put here. Yeah, here is. So one option is to create the faces of our wall. There is something that Pufferfish offers. There is a polyline to mesh component. In this case, it won't work because we have this curve inside a curve. However, if you had something like our first case where we had this on the ground, then this creates from a polyline, it creates directly a mesh, and it never goes through a BWrap. So you have as a result already a mesh. However, if you have a window or a geometry inside this geometry, then in this case I'm gonna use the mesh BWrap component. But I'm not meshing all of these solid, but I'm just meshing one of the faces. And then I'm using this boundary, moving it in the Z direction, the same wall thickness. And then with that, so I have my two polylines, the same that we had here. We have a list of polylines. And then with this list of polylines, I use the loft mesh component that we used also there in the other example. And with that, I create my sides without going through a BWrap. And then having this, I can move this down, put my sides, and basically I created my BWrap, my mesh from scratch without never going through a BWrap. And then when I position this, then I have here my wall positioned as a mesh, ready to be rendered by the online viewer. So this is for this option. And then for the second option, so our drilling holes, one is that we had here our five surfaces with the different holes, the standard ones. And here, instead of creating this, we're gonna create the meshes. Instead of creating the surfaces, we're gonna create the meshes. So it's basically the same principle, but we go by using a mesh. So here, for example, instead of using the circle component that we have here, because this creates a planar curve, we want to, again, to create a polyline, we need points. Therefore, in this case, I'm using the polygon component, which is gonna create by default polylines with these different radiuses. And then with that, I can create my mesh, and I can, and with that, I have control over how many points each of our drilling holes have. And this is just for visualization purposes. So here, for example, I'm controlling the amount of points based on the standard drilling radius. I could maybe go even beyond that and make it even more optimal. So, for example, here you could say, okay, maybe if people is looking from if they don't go to the detail of looking at it, but they just want to see the general view of the wall, then that would be good enough. So if we put this into here, into our geometry in our C# component, and then we use so this is again baking these transformations inside our geometry. So we have here as output also just 4 meshes, very small meshes, and then we use the display component. We put here the display component, and then we have all of our circles. And as you can see, these ones that were very small, these ones are very low poly. But if this is part of a very big piece of geometry, then the difference will almost not be noticed. So if I go Control M to get rid of our looking at the different seams, the different edges of our mesh, then you can see that everything looks like a complete single solid, even though we know that is constructed by smaller, simpler pieces of geometry. Instead of having here this one that you actually have to move your surfaces, and then you will have to mesh them. So that's a second step. So just not move them, but now mesh them and then join them. In this one, you don't need to do that because everything will look like a single group of geometry. And in another part of your definition, you could have all of your circles that are going to be exported by the user for production, for example. We will look into that more in detail on Friday. So yeah, that's basically how you would mesh these walls instead of going through a BRAP and then send a mesh to your online application. This drilling wall and this house, for example, in these 2 examples. And that's it. Is there any other questions?
Well, no, not really linked to the topic, so it's perfect because we are on time today, exactly on time.
Okay,
so
then I just want to do a little a quick thing here to link to our challenges, to our Rift Table version 1. So if we go to the Rift Table version 1, we can look at the different challenges. Number 1. So for example, here we have a solid difference that takes 2.1 seconds, and I'm asking you, is it necessary to make a solid difference to display the product? Is it really necessary to have this? Here we have another one. Again, we are using a solid intersection. So I'm asking you if this is really necessary to do. And then I also give you an option. So instead of doing this this solid intersection, you could actually use, in this case, for example, the curved line component. In this case, is a C#. We will explain more in detail this tomorrow at the beginning when we show the solution for this. And the same here, where we use BRAP to BRAP intersection that takes 127 milliseconds. And then here you should try and change that with a curved line intersection, the C# script. And yeah, I think there is other ones. Yeah, here is something similar where we have a BRAP and a plane. And here that we actually have all of these as BRAP, and we actually need to have that as mesh. So try creating a mesh with the components that we use today. Try to create a mesh directly instead of creating a BRAP for the displaying of the Rift table. And that's it.
Exactly. So yes. So if you look at all these points that Edwin just talked, you'll be able to apply today's concepts and make the first step of optimization for this like table model that we'll study on day 3. And I'll sound like my old teachers, but doing it yourself is always a better way to learn than just listening So yeah, if you have time to do it, I think that's amazing.
And then when we post that in the forum,
yeah,
here...
right now we're gonna post a new topic. So there's already the topics for last week's challenges, but let's just create new topics with the new files. I think that's
correct. Yeah, but I just wanted to show that, as you can see here, some of our participants last week, they actually uploaded that version, the version that they created, so that and then we showed them, we showed these versions as an example of how our participants had understood the concepts that we were teaching.
Yeah, it's a great moment where we can really involve everyone. So so that's always appreciated. Yeah.
Okay.
Okay, but besides this, thank you so much for joining us on this first day. It was amazing again. And yeah, so now we'll stay online. We'll officially close the session. We don't want 90 minutes, so we respect your time. But if you have more time now and you want to ask more questions and discuss with us, we'll stay online for about half an hour more. So thanks again to everyone.
Thanks everyone for joining, and see you tomorrow in the second day.
Mm-hmm. All right, so for our friends that are staying a bit longer, can you use Weaverbird for remeshing?
I don't think so. I have used it. I haven't used it that much, to be honest, Weaverbird, because we don't work that much with jewelry internally. So there is jewelries that already have their own Grasshopper team. Therefore, they are experts in creating this kind of definitions with Weaverbird. But in the project that we have used them, I haven't really seen a way to rebuild it with Weaverbird. What about you, Matthew?
No, it's Weaverbird is good to create meshes from scratch, really control what meshes you create, and also for all the sub-D components that allow to sub-D. So you can start from a very coarse mesh, very low poly, and refine it and make it very smooth. But really for remeshing per se, it's not really meant for it. In Rhino 7, so the current whip, you'll have the new quad meshing components. I think, at least it's going to be Rhino functions, but I'm assuming there's going to be Grasshopper components for them. And that's going to be a great way to remesh to a clean quad mesh, some extent, existing meshes. Yeah. So is that Grasshopper file with all the C# components available? Yes, we'll post it. I'll try to do it even now during the Q&A, so in a few minutes, but it's going to be on the forum very, very soon. Several users ask again about we said that we would give a solution for engraving that's a bit more efficient than using Boolean operations. So we don't have one exactly ready, but you would among others, you would lose the loft mesh component, right? The loft mesh script and some other like optimized meshing components. Edwin, I don't know if you have a bit more details about this.
Yeah, so that means that you actually see the engraving inside the say the ring, for example. So what we normally do is, first of all, for creating the actual curves, we have a C# component that actually creates curves from input text, but create meshes and curves from input text, but internalized ones. So instead of one solution is, instead of creating meshes from scratch, you could have, for example, the alphabet in whatever font that you need, and then from that you can actually pick your meshes. So if we check here, let me find it out. So basically we have stored all the alphabet with the meshes, and instead of actually creating the mesh from scratch, you pick all of the different parts of your engraving, and then you would, for example, create the hole, just the hole in your piece of geometry, and create the engraving. I will try to I mean, maybe it doesn't make sense right now as I explained, but I will try to create a quick definition, and I will post it also in the forum.
Yeah, let's post it on the forum. So I'll post even in the chat now the link. I just opened the new topic in the forum, so you can already find all the links there. And we can move on to this question that was asked a long time ago, because it was about scripting. We did also last week. Will a definition work faster if you use Python scripting or C# scripting? So in general, there's a few differences between Python and C# that are relevant. Python is interpreted on the fly, so it's always going to perform the same whether you just open your definition and for further runs of the definition. Whereas C# scripts need to be compiled the first time they run, and then they run a bit faster because they're compiled. So in any case, Python will be more reliable over time, and C# will perform better on the long run. But the first time you're going to send a request to the server, it's going to take a bit longer because you need to compile it. In any case, it's not really different. You can achieve the same functionalities more or less with them. And in general, you can do powerful things with scripts. But for these reasons, the interpretation or compilation, it's not the most efficient to run. It's more efficient if you use existing plugins to achieve what you need to do. Or, you can't install your own plugins on our shared systems, but we have like specific separate systems where you can, create your own plugins, compile them, and install them on our systems. And that's always going to be faster than using scripts in general.
Yeah.
So yeah, that's the general answer about scripts.
And just remember, everyone, that I see some questions in the chat. Please remember that you need to make your questions in the Q&A interface. Yeah,
I try to follow in the chat, but sometimes it's a bit hard. We have a lot of comments.
You need to make your questions in the Q&A interface, not in the chat. In the chat is more general to communicate with everyone.
Yeah. Just a quick one. We will be exploring how texture mapping for visualization works on ShapeDiver. Not really the core of this webinar. We really focus on optimizing and cloud applications. But on day 3, Edwin will briefly present some texture options. But in general, this is a more specific ShapeDiver question. And for this, you should really check our YouTube channel, the ShapeDiver YouTube channel, because we uploaded a series of tutorials that taking from zero if you don't know anything about ShapeDiver, and they tell you everything about a bit of like the concept we saw today very briefly. But then you have so episode 2 of our tutorial series is exactly about this, about texturing, texture mapping. And then you have more and more data I/O and a lot of topics are covered. So really, I recommend you look at those videos if you have like ShapeDiver specific questions. Exactly.
Yes, so youtube.com/ShapeDiver, or you can also check our blog in shapediver.com/blog. There you can also find, especially for Grasshopper developers, there is a section called the ShapeDiver Basics, and there you can find different blog posts specific to each of these subjects. For example, here we have the one regarding texture mapping explained. But the main thing to have into account is that we support a third-party plugin called Human, which has something called texture mapping. And then here we support all of these components for texture mapping. For example, here we have also extended our loft mesh component. And this one also now supports that you can input U texture size and UV texture size, basically. And then this will automatically also create texture coordinates inside your mesh. So you will get directly your whatever shape you have, organic shape, you will have it already texture mapped with this C# component.
Yes.
Okay.
Okay. At what point? I think this is interesting. I'm not sure how we could take 2 hours to answer it, but let's try to be brief. At what point in the design process do you switch from prototyping the definition to optimizing it? How do you assess when it's worth to do that, aside from cloud applications, of course?
So in my case, for example, I spend normally when it comes to the design phase, I mean, the problem is that it's so sub. It depends on the project.
Yeah.
But especially after a while, you have to at least, let's say, every day that I'm working on Grasshopper, I spend at least 1 hour cleaning up my definition. So cleaning up is not just includes optimizing, but like actually organizing my inputs and outputs. So for example, as you can see here, I always have all of my inputs here, and I always have something like this. So I have all of my inputs here, and I have something that I call my ingredients. So instead of having everything from here, I have my ingredients here. So it's the same inputs here. But then if I want to, I need the wall size for something, then I can just take this wall size and use it somewhere else. And I'm not just pulling everything directly from here and making it like a mess with all these wires. I have everything very organized. And also, well, especially if you work in teams, it's very important so that everyone can understand quickly your definition. And second of all, because when you start to organize your definition, you start to see, I actually can, in this part of my definition, do something better in terms of optimization or in terms of, in general, in a better way to do it. So then I normally spend at least an hour a day if I'm doing a design process. To just think on how to make this better, faster. But anyways, again, this is so subject to what project you are looking at.
Yeah, but I think it's also a matter of habit. So at this point, if you know you can do better than Boolean operations from the start, you're not going to use them at first to be faster and then switch. You might from the start working with other methods. And then streamline everything from the beginning.
Yeah. Mm-hmm.
Yeah. Do you have experience with mesh colors changing calculation efficiencies? I'm not sure exactly what it meant here. You can use mesh colors on ShapeDiver in general, like when when you export meshes from the definition. In terms of it's a good way to render something fast, or like to have all these color gradients on meshes, etc. In general, it's just, of course, less optimal when you transfer data, because you have one color per vertex, so the mesh almost doubles sizes, or like at least like 50% more if you have normals as well in the mesh. So that's like the only drawback to using mesh colors in the context of cloud applications, is that the file just like weighs a lot more. Can you explain a little bit about pufferfish? I mean, you can do a very quick presentation about what pufferfish is.
I mean, the thing is that all of these are third-party plugins that we support. Yeah. This pufferfish was created by, let me remember.
Michael Pryor.
Michael Pryor, yeah, I had it here. Yeah, actually was the person that did this post, Michael Pryor. So he is the developer of this third-party application. And basically, it has a lot of extensions to what you normally, what Grasshopper offers as default. So a lot of extensions to work with your data, work with domains, curves. So for example, this twinning, compatibilize. So it's just it gives you extended tools to work in Grasshopper. If you want to know which third-party applications we support, you can go to support.shapediver.com, and here in the ShapeDiver plugin, there is one part where we have something that is called list of supported third-party Grasshopper plugins, and here you can see all of their third-party Grasshopper plugins that we support, which of course includes the pufferfish, this dentro that we talk about that makes a bit faster the Boolean operations. Different ones. FAQs we will use, for example, on Friday, as well as OpenNest is another. Human that we just talked about. Human. We even support Kangaroo, Launchbot, etc., etc. So here OpenNest that we'll use on Friday. So you can see here pufferfish. You can see here all of the different third-party applications that we support.
Mm-hmm. All right. When will the record be available? I missed a little part, so it would be good to catch up before tomorrow. So unfortunately, we won't have the record by then. We need to process it, edit it, etc. So it's a bit short. But just know that first, if you look at the challenges that are on the forum, and also at the beginning of tomorrow, Edwin will go back on the concepts we saw, and he's going to give answers for the table, how to optimize it using today's concepts. So that's one thing. And the second thing is that anyways, the topics we'll see tomorrow and on Friday, they're not, you know, it's not really the sequel. It's different topics, different ways to optimize, and tomorrow is more about data management. So you can follow tomorrow, even if you didn't follow today, actually. And the recordings will be available, you know, later this month, hopefully by the end of next week, I think. I'm curious about some smaller optimization things, like using polygon center instead of area for centroids, or casting text in panels to floats. Do you try to get everything the most optimized, or only focus on the big issues?
On the what? Sorry.
On the big issues, like the main.
I mean, you can go as far as you want. The thing is that, of course, here we're working with a very simple script, but when your scripts start to get bigger and bigger and bigger and bigger, then each of these details will count to the final computation count. So we do try to use the best practices from the little detail to the biggest one, especially if we know that this script will become into a huge script. Again, because then all of these little details will count in the final computation time. So we have done very complex projects that are still very optimized, because we keep into account all of these optimizations. So regarding the polygon one, so it depends how you do that, because for example here there is that component that you are talking about. I think is this one, the one that you're talking about, polygon center. Yeah. The problem is that this one anyways also outputs the area centroid. So this one will anyways calculate the area, I believe, or not, Mathieu? Because anyways it calculates there. Yeah, there we go. Yeah, it's taking even more, because this one also outputs the area centroid. So an option would be, for example, let's do a quick experiment here. So if we explode each of these curves, anyways, this already takes a bit. Yeah, I mean, it's better to, because one option is to take the average of these points, and then the average of these points will give you also the sorry, of these points will give you also the centroid. But again, well, you can see that then we're making everything even slower. So it depends for what you require. And if you don't require the area, then there is ways that you can also try to compute the centroid without having to go through these components. Again, mathematics sometimes is your best friend in these cases.
Yeah. Mm-hmm. Yeah, in general, just like as a last precision of about this, you know, how far you optimize depends on your needs for the project, right? So if you have something that's not optimized, but it's still, you know, fast enough for what you need, or computes without issues, then that's fine. But yeah, as your definition grows, you might see that details start to matter. Would the general guidelines be to work with the simplest primitives, starting at number, math, point, line, and up? I mean, yeah, in general, right? I don't know what you would say, Edwin, but basically, you know, even the first example that Edwin showed, his latest version started with BRUT, but you could also start by creating your own mesh, right? Like point by point. That would always be the most efficient. Of course, the complexity of doing that in most cases is very high. So as long as you can keep the simplest objects and work with them, that's great. Yeah. But it's not always possible, yeah.
Yeah, for example, there is also a component called here in the mesh. You have this component called construct mesh, where you can actually take each of these vertices, give the description of each of these faces, and even add colors. So this is quite optimal. And this is basically what we do with this C#. But with this C#, we automatically generate the faces, for example. So if you don't know how this faces logic works, then, because basically a polyline is a list of points. So here you are giving, in this case, for example, the list of points to your input. So that will be the vertices input. But then you need to also take into account the order of the faces. And then if you know how this works, then you can create each of these faces from scratch, and then you can have the list of faces, and then you can have you can construct your mesh from scratch. But with this one, let's say we save a bit of that work, and we automatically generate with this C# these faces the faces logic.
Mm-hmm. Okay, will ShapeDiver Squid be used? It's not loading for me. .NET version is newer than Grasshopper. So yes, we've heard some people had, it depends on which version of Rhino you're using. Squid, you might have trouble loading the Squid components. Please check on the forums, several discussions about this, and also ask your question if you have trouble. We will not use Squid tomorrow, but we'll briefly talk about it on day 3. So it's good if you can make it work.
Yeah, in the forum, there is different topics that talk about some people having problems with that. So try to look in the forum about that, and there we give the solution, and people have been able to load this Squid. So so just try to look in the forum about that.
Yeah. So 2 quick questions that we already answered, but just to make it clear, what software do you use for sketching on the live webinar? Was it Epic Pen? Is that how it's called?
Yeah, correct.
Epic Pen.
So and just here I found it. Just 1 second. Here I found it. The issue is called fail to install Squid ShapeDiver edition, and then here Mathieu gives an answer of how to solve that, and they actually got it to work. So,
I mean, I think one common problem is if you had a previous version of the ShapeDiver plugin, you should really remove all the files, everything you have, because from version 1.6, which is the link we included in the email, version 1.6 has an installer that installs everything, wipes everything, and Squid is included in this along with some other plugins. So yeah, if you install the latest version and you had previous versions before, try to really remove manually everything you had and clean up everything before you do. Yeah, another quick question, was this recorded and can we rewatch it later? So yes, it's recorded, and yeah, no date, but hopefully by the end of next week, we'll have a recording for you. And I think it's a nice last question. You already saw it, I think, because that's what you're showing. What was the most challenging project you've worked on? Can you share with us which parts made it difficult for you?
Well, in this case, this is one of them. Depends on the complexity. I mean, on where you put the complexity. For example, we are working also in another project right now for a company in Austria. They do cancellation noise walls. Which you would think that is a very simple product. However, it is very simple in terms of geometry, but it's not very simple in terms of product logic, because we are automating all their process of creating all of these cancellation walls parts. So all of their parts are going to be, all of their process of creating these walls is going to be automated, and therefore it becomes very complex. And we even created a custom plugin for them, a custom Grasshopper plugin for them. In this case, it's a different kind of complexity in this model that I'm showing right now. It's a complexity regarding more of the geometry, but also the way you interact with the geometry in the online application, and also that this also generates all of the production files. So after this is a wall that is already built, like it was built like 2 weeks ago or 1 week ago. It's a wall that is built in the offices of Oracle in the US. And this wall basically, this was a one-off wall where the designers were going to come here and start to do some little tweaks about the wall, start to move some control points to tweak the way that the wave of the design goes. And then it's almost like a mini Grasshopper, mini Grasshopper, where you can actually save your changes, undo your changes, flatten the wall, and then at the end of everything, you can actually export all the production files of this wall. So, for example, here you can see that there is a problem. Yeah, but basically, all of this wall was created with very optimized options, and then when you save everything, you can actually go export wall, and then you can actually get all of the different pieces laid down, nested, ready for production. and with the different, for example, numbers of okay, this is piece 1, piece 2, piece 3, so they can organize when they start to construct this wall. Here we have edit maximum curve point and edit cut curve. So there is like different control curves that we have in this wall where you can edit different parts of the wall. And yeah, basically, and the most challenging part of this one was to keep optimize the nesting of the wall, because of course a lot of pieces, because it's not just all of these that you see here in front, but on the back you have basically repeated all of these things, so it's double the amount of pieces, and then you have to make all of this process as optimal as possible.
Yeah, exactly. So I think that's a good example of like a bigger scale project, and we even have like bigger scale than this, I think, but that's a good example of complexity. Of course, you can also, some projects are really complex, but for smaller products, you wouldn't imagine, but you can check on our website some jewelry or furniture, configurators. Some of them are necessitated a lot of data management and optimization. So all the concepts that we talk about in the webinar. But yeah, that was, I think, a really nice question to close the session today. So again, thanks a million for being there with us. And yeah, don't miss tomorrow's session. We'll talk about data management, so tree management, and using JSON objects to really communicate data flows between Grasshopper and a web application. So yeah, have a nice evening or rest of the day, depending on where you are, and see you tomorrow.
Yeah, thank you everyone for joining, and see you tomorrow with the data trees management.
Bye-bye.
Thank you very much. Ciao, ciao.